He worked at the NRAO, the National Radio Astronomy Observatory in New Mexico, at the Museum of Natural History of New York, and Columbia University, also New York, before moving here to Taiwan and starting his work at Academia Sinica. He works on the field of exomoons, surprise, surprise, and he works on the machine learning techniques to explore data. So give a big hand to Alex Teachey.
谢谢谢谢，大家好。不好意思，我的中文不好，所以我需要说英文。Let's see how we do this. Oh, right there. Oh man, I'm like blind without my glasses. All right, hey, how's it going, everyone? Thanks for coming out. My name's Alex. Thanks, Lampo, for that introduction. So I'm going to tell you tonight about work that I do and work that other people have been doing too. Looking for exomoons. So you may have heard of exoplanets. These are planets that orbit other stars, right? So we orbit a star, of course. The sun is a star. There are something like a few 100 billion stars in the Milky Way galaxy. And over the last few decades, we have discovered thousands of planets orbiting some of those other stars. So what I do is I look for the moons of those planets. We call those planets exoplanets, and so we call the moons of the exoplanets exomoons. So I'm going to tell you about it. I think it's really cool work. Obviously, I really dig it, and I hope I will convince you that it's worth doing and kind of interesting. But remains to be seen. We'll see how it goes. Why do we care about this work? I think this is an important place to start in science in general, and especially in astronomy, right? We're not inventing a vaccine. We're not curing some disease. In astronomy especially, it's like, why do we really need to do this work? It seems kind of like maybe, it's interesting, but why do we care? We've got to ask these questions. When it comes to moons, they're awesome. That's not really the extent of my answer, but I think moons is something that we've been thinking about for thousands of years. Cultures all around the world. The moon is central. It's in mythology. We've looked up to it. We've used it for timekeeping, and of course we landed on the moon in 1969, and this is arguably the pinnacle of human achievement. And this is an achievement that people will be talking about really thousands of years from now. And so the moon is central to our thinking, and is really an amazing place, and I hope we go back there soon. But it's not just because it's cool. We really do have some questions to answer here. When we're looking at these exoplanets, of course we're learning more about those exoplanets. Those systems are interesting in their own right. We just want to know everything that we can possibly learn about these worlds out there. But it's also really a mirror to our own solar system, right? I mean, where do we fit in our galaxy? In what ways are we ordinary? What ways are we extraordinary? That's very much an open question. And so when we're looking at these systems, we're learning more about those systems, but learning more about ourselves in the process. There's also a very important dialogue in astronomy between observers and theorists. This is kind of like the two major categories of astronomers. Some people, they put physics in the computer and they do a lot of math and they try to figure out what's happening from a theoretical perspective. Me, I'm an observer. We use telescopes and we take data from the sky and we try to understand that data. But we really can't work in isolation. We really need to be talking to one another. And the theorists, they can really get out ahead of us and make all kinds of predictions about what we should see out there, but it takes us as observers to kind of basically catch up and find these things and see, are the theorists right or are they not right? Do they have a complete picture, an incomplete picture about what's going on there? And so, like I say, the theorists are way out ahead of us when it comes to understanding planets and moons, but we've got to test those predictions against observations. So astronomers are interested, of course, in answering lots of different questions. Astronomers do all kinds of things, obviously. What happened to the Big Bang? Black holes, what's going on? How do galaxies form, right? There's so many different kinds of astronomers do so many different kind of things. But exoplanet folks, like me, and actually some other folks here in the room and at Academia Sinica, we're interested in questions of how stars form and how planetary systems form. We've got some good ideas about how all this works, but the details, there's still very much many open questions, and we're trying to understand what happens when planetary systems form. Obviously they do, right? Our solar system is here, other planetary systems are out there, but how you actually make those, there's a lot of questions, believe it or not. And we're seeing, just in the last 10 or 15 years or so, we're getting these incredible images from these radio telescopes. This is from ALMA mostly. This is a telescope down in Chile. And we are imaging for the first time these proto-planetary disks. These are solar systems, like our own, other planetary systems in the process of formation. These are disks of material swirling around a central star. And you can see at a glance how different they are, right? I mean, they broadly look similar, but there's also a lot of differences there. And so already we're learning a lot about how these systems form, but we always want to come in every angle that we can think of. This is just one piece of understanding how planetary systems form. And when we see these planetary systems, of course, when we look at a star, we're seeing a snapshot in time, right? That star is 2 billion years old, that star is 7 billion years old, right? We can tell what's going on in that system at that given time, but we really need a census of all of these different stars at different stages in their lifetime to get a sense of how these systems are born and evolve and eventually die. And so moons are, of course, formed at the same time basically that planets are formed. It's all happening at the same time, right? The star is born, we've got a disk of material swirling around the star, and the planets are getting born in this disk of material. And then the moons, similarly, are being formed right at the same time. And there's basically three mechanisms, three different ways that we think that you can get moons. The first way is what we call the giant impact scenario. This is how we think we got our own moon, for example. The general thinking is that there was a giant planet about the size of Mars that slammed into the Earth and blew off all of this material, and that material was swirling around and coalesced and formed our moon, right? So that's one way that you can make a moon. It's not clear how often that happens, so that's an open question. The second way is a capture scenario, right? This is an object that's free floating, it's doing its own thing, and then it gets too close to the planet, right? And it gets pulled in gravitationally, and so it wasn't a moon to start with, but then it becomes a moon because it gets pulled in gravitationally to orbit the planet. And the example that we see in our solar system, or one example that we see in our solar system, is Neptune's largest moon called Triton. Has all these sort of telltale signatures. It's orbiting the wrong way and it's tilted way up. So we think that Triton's largest moon was actually captured from the Kuiper belt, which is sort of like a second asteroid belt way out far away from the sun, of which Pluto, by the way, is a member. And then the final way is formation in a circumplanetary disk, a disk of material swirling around the planet. Very much the way that planets form in a disk of material around the star, so too is there a disk of material swirling around the planet, and the moons are formed in this disk. So this is basically the three main ways that we think that you can make moons in our solar system, and probably other planetary systems as well. But we could still be surprised, right? Until we start seeing these worlds out there. Maybe there's other stuff going on that we just haven't even dreamt up yet. We also think that moons might be able to trace the histories of planets migrating around. So it turns out that where we see the planets in our solar system today, Jupiter and Saturn, Uranus and Neptune, they're pretty far away from the star, from the sun. It turns out that, the general thinking is that these planets weren't always there, but in fact they migrated closer to the sun at one point and they moved farther out again. So, if these planets have moons, what happens to those moons? Obviously we see Jupiter and Saturn and Uranus and Neptune, they have a whole bunch of moons, right? So did they have more moons? What was going on with those moons, right? Because you're playing sort of cosmic billiards here. You're kind of fooling around with stuff. So maybe something happens to the moons when these planets form, or we're seeing like a second generation of moons, right? So we think that moons could sort of fill in the gaps of this migrational history. Now, when you look at the moons in our solar system, these are major worlds. They're really astonishing places. You just saw in the second round of the quiz, right? You could see at a glance how different all of these moons are, right? Major worlds. This is Titan. This is the largest moon of Saturn. This is not what it would look like to the eye. It's sort of a false color image. But this is an incredible moon. It has a thick atmosphere, believe it or not, and it has methane and ethane raining down from the sky and collecting in pools on the surface. There's liquid methane on the surface. It's actually the only other place in the solar system where we have liquid that's stable on the surface. It's extremely cold. You don't have liquid methane on the Earth, just lying around. There's no liquid methane. But you do have liquid methane on the surface on Titan. So this is a place that people, were very interested in visiting. We actually have visited it once. We landed a spacecraft on Titan, and we're going back. Can't wait for that mission. It's going to be another 10 or 15 years or so. I hope I'm still around. Probably will be, but it's going to be an incredible mission. So stay tuned on that one. Titan is an amazing place. But you can just see here's another look at these moons. Geologically diverse. Just take a look at the surfaces of all of these things. They look so different from one another. They look so different from our own moon. Here's our moon, for example, right? It's not the largest one. We've got moons in our solar system. This is a moon of Jupiter, Ganymede, moon of Saturn, Titan, another one of Jupiter, Callisto, another moon of Jupiter called Io. Here's Europa down here. This is Triton. This is the moon that I was telling you about, the largest moon of Neptune. So just look how different they are. Rocks and ice. These are really amazing places. And I always tell people, you grew up knowing the 8 or 9 planets, depending on your preference. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune, and maybe Pluto in parentheses. And if these worlds were orbiting the sun directly rather than orbiting a planet, we would have all grown up knowing their names, because they are just as interesting, I would argue, as Mercury and Venus and Earth and Mars. And maybe not as interesting as Earth. I think Earth is the most interesting planet in the solar system, but these moons, they give the other planets a run for their money because they're very interesting places. There's also abundant water on some of these moons, including liquid water in some cases. So check out this image. This is the Earth, of course. They've stripped all of the water off of the surface of the Earth and they put it in this little sphere right here. Now over here to the left, that's Europa. That's a moon of Jupiter. You can see it's much smaller than the Earth, but they've taken the water from Europa and put it in that little blue sphere there. So there's more water on Europa than there is on the Earth. And even though it's covered in ice, the planetary scientists tell us that there is an ocean of liquid water underneath the surface of Europa. So what's going on in that ocean? I mean, it's covered in ice. And this is another destination that NASA and folks like this are very interested in visiting. What is going on underneath the surface of Europa? It's very exciting. These moons have internal heating as well. Of course, we have internal heating on the Earth, right? This is how we have volcanoes and geysers and hot springs and Beto and places like that. That's a different mechanism. We have a hot core. These moons are getting squeezed gravitationally by their host planets. And so the planets are injecting energy into these moons. And so you can get similar kind of things, geysers. These are icy sort of geysers. They'll call them like cryovolcanoes. This is the south pole of one of Saturn's moons called Enceladus. And so these are spewing ice hundreds of kilometers out into space. And so this is really exciting because you can actually fly a spacecraft through these plumes of ice and sample what's in that stuff. So you don't even have to land on the surface to see what's going on underneath. You can kind of just test these plumes and see what's in them. What is it made of? What's going on? And by the way, we also think that there's liquid water under the surface of this moon. This is Enceladus once again. And so we have seen these kind of things on, that's Io, that sort of yellow and reddish moon, the innermost big moon of Jupiter. We've seen these volcanoes of sulfur spewing off the surface there. Here's another look at Enceladus. Just look how, this is the size of the moon, and it's spewing this material off. And this is Europa, another moon of Jupiter. This is obviously a composite image. This is a plume that was imaged by the Hubble Space Telescope. This is from a spacecraft that visited Jupiter, and this pixely stuff was imaged by Hubble Space Telescope. So you can imagine, you've got internal heating, you've got liquid water under the surface. You can have something like what we see on the Earth, called these black smokers, right? Oceanographers for a long time thought that the bottom of the Earth's oceans must be just totally desolate places, right? Because it's extremely cold, extremely high pressures, and pitch black, of course. And then they found these black smokers, and these were sort of like oases on the bottom of Earth's ocean. So you put it all together. We have liquid water, and we have a heat source. We're sort of veering towards this very interesting possibility that maybe there's life on these moons. Now, it's very possible, right? And some of these moons are interesting places, we think, to look in our own solar system for life. And so the thinking goes that if these moons in our solar system are attractive places to look for life, maybe also these exomoons similarly could be great places to look for life. And I'll say one more thing about that. We have these things called habitable zones, right? If you get close to the sun, it's very hot. If you get far away from the sun, it's very cold, right? So there's a sort of a happy medium called the habitable zone, or some people call it the Goldilocks zone. You'll hear it called that. This sort of green area where liquid water, it's just the right temperature that liquid water can exist on the surface. So you can imagine if there's a planet kind of like Jupiter, that planet may not be a very good place to look for life. But if that if that planet has a moon, then maybe that moon could be some kind of Earth-like. That's very much an open question, but it could be. And if that's the case, this could expand significantly the amount of real estate available for life in our galaxy. So how do we actually go about looking for them? I hope I've convinced you by now that these moons are interesting places and worth looking for. So how do we actually look for them? First thing you might think of is let's just take a picture, right? Let's just point the telescope at it and let's photograph it. And it's a good thought. This is about the state of the art. These little pixels. Now astronomers this is an absolutely dazzling video taken over the course of 6 or 7 years of this planet orbiting that star, and we're seeing it basically edge on, and they've imaged it again and again and again. And we're looking at a planet in orbit around another star. It's really amazing video. We can only really produce images like this for a handful of stars, believe it or not. Only the stars that are pretty close to us. And actually that planet is, I believe, shining by its own light, shining by its own heat, because it's very young, so it's actually quite warm, and so we're seeing the heat of that star. That's not reflected light, it's shining by its own light. In the infrared, I think. So you can see that if this planet has a moon, it's going to be very hard to see, at least in the short term. Now, it could be that with improvements in technology, we might do better in the future, and so these are simulations of what we might see with a future telescope called LUVOIR. This telescope is a good 15, 20 years down the line, if they build it at all. It hasn't even been approved yet. But this is astonishing. This is what LUVOIR might be able to see if it were looking at our own solar system from many light years away. And so you can imagine with images like this, we might be getting to the point where we could actually start seeing hints of exomoons. But that's a ways down the line. In the meantime, I've got to have a career. I can't wait 20 years for that data, so we've got to come up with more clever approaches. And so really the best way of doing this work, I would argue, is looking for these things called transits. And so that's what we're looking at here. This is the sun, of course, and what you're seeing there is the planet Venus transiting in front of in front of the sun. This was probably taken, I'm not sure, 2012 is my guess. Maybe, unless it was from a spacecraft that caught it at a different time. 2012, there was a transit of Venus, and I hope you saw it in 2012, because the next one's not until 2117. So, I don't know how many of us will be around in 2117. I probably will not be. But this was amazing. So you can see what happens here. The planet passes in front of the star from our point of view, and so it blocks out a little bit of the light. Now this is a very rare event when we see it, because we're embedded in the solar system. You've got to get the geometry right in order to see Venus pass in front of the sun from our point of view. But if you're looking at other stars, that geometry is much more convenient, and actually this is a way that we have discovered thousands of exoplanets. That we just happen to see them in the right orientation, and so the planet passes in front of the star from our point of view, and it blocks out a little bit of the light. I mean, I'm talking very little bit of light. It's like order of 1% or less, maybe 0.1% of the light is blocked out. And fortunately, we have telescopes that are sensitive enough that we can actually see this. So you can imagine if the planet now has a moon, then the planet is going to block out a little bit of light, and the moon is also going to block out an even smaller amount of light. And these moons are very, very small in some cases, can be much, much smaller than the planet. For example, Jupiter, largest planet in our solar system, it has 4 big moons. Those moons, as I showed you before, much smaller than the Earth, right? Jupiter, you could fit 1,000 Earths inside Jupiter. So Jupiter, compared to the moon, is much, much, much bigger, and so we can see these planets, but spectacularly difficult to see the moons in some cases. Even though hope springs eternal, and so this is the work that I do. So we look, this is what the data look like. We monitor the brightness of those stars, just take picture after picture after picture after picture, over and over and over again, and you can measure how bright that star is, and then when the planet passes in front of the star, there's that dip that we're looking for. And the planet comes around again and again and again, so we see a dip, and another dip, and another dip, and another dip. And now if that planet has a moon, we'll see, again, a smaller dip from the moon, right? Here's the planet, and there's the moon. And here's the planet, and here's the moon. Now, you can see how noisy that data is. If I took away these lines, you probably wouldn't say like, oh yeah, definitely, moon, got it, you know. Very, very small signal. But nevertheless, these are the signals that we're looking for. So this is the kind of data that we get. And actually, it's kind of nice because the data that we use has more than one signal imprinted in it. We have those dips, right? But there's also these gravitational influences that the moon exerts on the planet, right? So you probably know that the planet is pulling on the moon gravitationally. What you might not know is that the moon is also pulling on the planet gravitationally, right? They're pulling on each other. And so what that means is that the moon wobbles around, all right? So the planet wobbles around. So the planet is going around the star, but because it's got a moon there, it kind of wobbles. And so what that means is that sometimes the transit comes early, and other times the transit comes late. And so we can see this. I mean, it's just maybe a couple of minutes swing on either side, but we can measure that. And actually, it will change the duration of these events as well. The moon can make the duration of these transits longer or shorter. And so there's really 3 signals all in this single data set that we're looking for. So that's really exciting. And we used mostly the Kepler Space Telescope for this work. Kepler was an amazing mission, and what it did was it spent 4.5 years staring at that one patch of sky, monitoring something like 200,000 stars, just staring at it and just taking readings from all of those stars again and again and again and again for 4.5 years. And this is what it would this is what it would see. And so that was an amazing mission. Kepler was incredible, and there's so much data to use. And actually, the mission itself ended several years ago, and we're still using this data. It's really a phenomenal data set, and I use it all the time, and it's amazing. And in the course of my work as a graduate student at Columbia, I identified potentially the first exomoon transiting ever. And this was what it looked like. We saw 3 transits of the planet, and we saw these secondary little dips. And we said, it looks like a moon. And we weren't positive there was a moon. It was tantalizing, but it wasn't enough to come out and say like, yes, we got it, it's definitely there. You know, in science, it doesn't really do you any good to like make a big claim that doesn't hold up, because everyone will crap all over you on Twitter these days. You know, before people would just crap on you in the literature, like who cares? But now it's like, you know, everybody's got a hot take on Twitter, and so you know, you really don't want to like get out ahead of something if you were like not really sure. So we saw this thing, we thought it was interesting, but wasn't enough to like make a big claim. So what do? You get more data, right? That's the astronomer's mantra: get more data, get more data. And so we asked for more data, and we got it on the Hubble Space Telescope. And this was a really incredible privilege of my career to get Hubble data. And they awarded us 40 hours to use Hubble. So it was making my observation for 40 hours, and I knew when it was happening. It was October 28th, 29th of 2017, and I just knew that it was up there and doing my thing. And you know, I had planned it months and months and months in advance, and then once like the date came, I was like, oh man, like did I get that right? And it was like way too late to make any changes, and I just like broke out in a cold sweat. But it was really cool to know that Hubble was up there observing my target in real time. It's like it's happening right now. It was pretty amazing. And so the thing about this Exomoon candidate was that it was potentially the first, like I said, and word got out that we were going to perform this observation. And before we even like performed the observation, people were writing articles about it. And you know, some people say all press is good press, but this was kind of nerve-wracking. I would not recommend this for anybody, because like everybody was just like, hey, is it there? Is it there? Is it there? And we got the Hubble data, and like I like logged in that morning to look at the data for the first time, and I had like emails from journalists being like, hey, did you find it? Is it there? And yeah, that shit went on for like a year. And you know, so that's like not the nicest way to do science, like people breathing down your neck every step of the way. So it was cool that people were so into it, but you know, I wouldn't wish this on anybody. But this is what the data looked like. Oh, is it going to show up? Internet.
Is it there?
Yeah. What?
Is it there?
There it is. All right. Yeah. It took some time to load. So yeah. So we took a single image with Hubble. This is Hubble data, and that's our target there in the middle. That's the star we're looking at. Just take a single image like that, but most of the images look like this. This is a movie, I'm hoping you can see. And we spread the light out across the detector. What that basically is like putting it through a prism. And so this is kind of like, it's very short wavelength range, but it's kind of like looking at a rainbow. And so you're looking at the star at a variety of different wavelengths. And so that helps you kind of understand more about what's going on with the star, and helps you kind of handle some of the systematic issues that Hubble has. Hubble's data is pretty challenging to work with. And so we take all that light from all of those images, and we make what we call a light curve, right? Just like what we were seeing before from Kepler. This is what we get. All of these different readings, how bright is the star? And so we see the dip from the planet, right? And we looked at this and we ran tons of tests. I mean, I spent a year working on this, believe it or not. And we saw two signals really that we thought was consistent with the moon. One of them was that the planet transit started a full 78 minutes earlier than expected, right? So that's those transit timing variations that I was telling you about, right? The planet is wobbling, right? So we saw that, and then we saw this little dip over here. Now we'd love to have much more data than we really know for sure, right? But this is 40 hours of Hubble data, right? And that's already like a huge amount of time to get on this telescope. So we saw the dip and we saw this wobble, and so we said, yeah, like we tried to rule it out as best we could, but we couldn't. You know, we spent a year working on it, and we said, yeah, it kind of looks like it's there. And we stopped a little short of being like, it's definitely there. And like astronomers didn't know what to do with that, because you basically always come out and you'd be like, yeah, we got it, like give us all the praise. And we were just like, yeah, like I think it's there. And you know, like I think some people thought we were trying to have it both ways, like we were trying to get the credit for the discovery without like putting our asses too far out on the line. That like if someone said like it's not there, we were just like, yeah, well we never said it was really there. We said it was like, looked like it was there. That's not what we were doing really. We were trying to be as intellectually honest as possible. Frankly, you know, I mean the data looked like it was there. The best we could say is like, yeah, it looks like it's there, but it's not totally conclusive, right? So that was the paper, and we actually made the cover of Science Advances, so that was pretty cool. you know, that's kind of a nice experience. But you know, I have to be honest with you that not everybody believes this result, and you know, so we had like clever people coming up on Twitter, just you know, like immediately making the same joke. Makes the same joke on Twitter. Like, haha, that's no moon. Yeah, got it. Good work. But you know, but that's how it goes, right? There's going to be people making jokes on Twitter, but more importantly, there's going to be serious scientists questioning your result, coming along and saying like, well, what about this? What about that? Could it be this? Could it be that? Could it be that? That's all part of the process, right? So you got to have a little bit of a thick skin. I don't want to defend it just because I did my work, frankly, and like because I did it, like I'm like, well, very easily could have made a mistake somewhere along the line, you know. Some scientists, we were talking about this earlier. Some scientists, like they are more convinced in the result because they did it. And other scientists, like me, I'm less convinced because I did it. Because I'm like, who am I? But you know, we did our best that we could, and you know, actually, we still think it might be there. We still think it's not proven, but you know, we've done additional work in the intervening years, and we still think, yeah, it actually looks like it could still be there. But other people disagree. There have been papers come out that question our result, and that's all part of the process. So, you know, where do we go from here? That's just one moon, right? This is one. I spent a couple of years of my life looking at one system. But that's, you know, there's tons of stars, hundreds of billions of stars in our galaxy alone. So where do we go from here? We got to look for more moons. We got to look at more stars and more planets and look for these moons. It's very challenging, but, you know, Kepler is an incredible space telescope, but we've got other data to go through. Huge amounts of data that nobody has touched, basically. More data, more targets, machine learning. Lapo mentioned I've been doing some machine learning. New techniques, kind of trying to dream up new ways of looking for moons. There's so much work to do, and actually very few people on the planet doing this work. So it's really gratifying to be able to do this. And so what I've been working on recently is using machine learning. It's a big buzzword in astronomy right now. Teaching a computer to look for these signals in a huge amount of data, because there is so much data. There's something like 200,000 light curves from Kepler alone. There's going to be millions of light curves from this telescope that's up there right now called TESS. And so, you know, that's a heck of a lot of data to go through, and so machine learning is a particularly powerful way of doing that. So, so that's what I'm working on right now. I've got a lot of cool stuff cooking. I hope I've convinced you that this is a cool work. So thank you very much for your attention, and if there's time, maybe I'll take some questions. Thank you. The whole time. It's astronomy on tap. I'm supposed to be like drinking my beer while I'm doing the talk. Yeah, question over there.
So you mentioned you've got 40 hours on Hubble telescope. I imagine there's not that many telescopes that are able to even look at these types of data. So how does that work? Like, all those exomoon scientists like just line up, or you apply for grants, or like how?
Yeah. So the question is, how does it work when you apply for Hubble time? There's a lot of people that won't use Hubble. Hubble gets used for all kinds of different science. When it comes to exoplanets, most of the work is actually being done to try to understand what's in the atmospheres of these planets. Astonishingly enough, you can figure out the chemical composition of these atmospheres with Hubble and those kind of instruments. So that's what most exoplanet people want to do, and they guard their time jealously. They don't want to give it to the Exomoon people. There's very few of us, right? There's just like so few people working on it. But the way you do it is you write a proposal, and you try to make your case. This is really important work, and you send it off. And Hubble is oversubscribed. This is the word that we use. It means many, many more people want to use it than can possibly be awarded the time. So I think there's something usually somewhere between 10 and 20 times as much requested time as can actually be awarded. So it was very special. I've since submitted several other proposals, and they don't get awarded, right? So you really have to make a strong case of why you have to do this. So, have to do this work. And then if they give you the time, then they assign you some scientists at the Space Telescope Institute to look over your shoulder and make sure you don't break this multi-billion-dollar telescope. Don't point it at the sun or anything like that. And there's just a little program where you type in all of your requirements for your observation, and you plan it out months in advance. And some people that were like, "Oh, did you go to NASA and like have like the joystick and point it there?" And like sometimes using telescopes, like you really are controlling it in real time, but not with Hubble. Hubble is planned months in advance. Yeah, it's a good question.
Are you involved in? Do you know of any citizen science projects to look at?
Citizen science projects.
That would definitely expand the effort. The audience of interest.
It's true. No, I don't know of any citizen science projects.
Well, you can start one.
I could. Yeah. Sounds like a lot of work. But yeah, no, it's a great idea. I mean, so folks know. Actually, this is one way that I really got enthusiastic about astronomy to begin with. You might have heard of this thing called Planet Hunters. It's this website where you can log on. Anybody can log on, and you can look at data from Kepler Space Telescope, and now I think they're also using test data. And you can look for planets yourself, right? And you flag these little events. You say, that looks like a planet. And if you correctly flag these planets, and other people have also flagged the planet, and they determined, yes, that actually is a planet, then you get your name on a scientific paper. You say you're a co-discoverer of that planet. So I found this Planet Hunters many years ago, long before I went into astronomy, and I was like telling all my friends, like, you can look for planets too, and everyone's like, yeah. Okay. Yeah, that's what I want to do with my time, Alex. So then I realized that I was a little special, and I wanted to. This is what I wanted to do with my time. So yeah, so crowdsourcing these kind of projects is very powerful, but it's hard, and I know excellent stuff.
Which one is the moon that you are showing on the cover of the journal?
Oh, that's just an artist's impression. Yeah, so I sometimes I have this slide in my talk about direct imaging. Sometimes people, I had a student one time. They had to all do presentations, and she brought in this thing. She was talking about this planet, and she had pulled up found an image of the planet online. And it looked something like this, and she was just like, this is an incredible exoplanet. It's got lakes, and it's got mountains, and it's got trees. And I said, well, how do we know all of that stuff? She said, well, just look at the picture. It's just like, it's right there. I mean, she thought this was a real image of an exoplanet. Which, not totally crazy, because honestly, they look so photorealistic these days. So if you look up a picture of a planet, show me Kepler 90 or whatever. And you can find pictures that maybe look pretty realistic, but those are all artistic renderings. Yes?
How many telescopes are currently looking for your exomoon? Just Hubble, or are there other telescopes that you're working with?
For my exomoon, none at the moment. So there was Kepler. Kepler is now dead. That operated from 2009 to 2013, I think. And then it had second life as this sort of secondary mission called K2. And there's a heck of a lot of data out there that I am planning to get to, but I haven't yet. And now there's TESS. TESS is really the new survey telescope for exoplanets. And it has kind of a different mission profile. I told you before, Kepler stared at one patch of sky, right, for 4.5 years. So that was really amazing, because you got 4.5 years worth of data for every star that it was looking at. TESS kind of takes a different approach. It looks at one patch of sky for like a month, and then it moves on, and a month and moves on, and kind of scans the whole sky. So we're getting data from the whole sky, which is incredible, but much shorter timelines there. So that's hard, especially since we think that these planets, if you look at Jupiter and Saturn, Uranus, and Neptune, they're very far away from the sun, and so they have very long orbital periods. So they come around very, very rarely. If you were looking for them in transit, they would be very rare. And so that means that for data like what we get from TESS, it's very difficult to find those very cold planets. You see a lot of planets that are really close in and orbiting very fast, but not those planets that are far away. So Hubble obviously still works, and we still keep it in mind if we ever really want to go after something. Hubble was about 4 or 5 times more sensitive than Kepler was. And now, hopefully, we will have very soon this new telescope, James Webb Space Telescope, JWST for short, and that is going to be several times improvement on Hubble's sensitivity. So, would love to get that data eventually, but it's going to be very hard to come by. Everybody wants JWST data, so we'll have to make a very strong case. Cool. Any other questions? Right. All right, I think that's it. I'll be around afterward. You got more questions. Thanks for your attention. I appreciate it. Thanks so much.
Thank you very much, Alex.